So let's get to architecture. So how can we build, or how can we even assess what architectures are good for data-intensive computing? And it's worthwhile to go back to Amdahl. So Jim Amdahl was the designer of IBM's mainframes, and he wrote down a couple of laws and rules of thumb for a balanced system in the 60s. And he found that in a real-life scenario, a system was happy, the CPU was happily humming along, if we were able to feed about 1 bit of I/O per sec for each instruction. And people later in the 90s, that the machines with a multi-tiered cache hierarchy emerged, started to say that, okay, these are not really relevant because we have the cache locality. And so data is not necessarily moving through this whole pipeline. But once we have again petabytes and exabytes, all this data is coming from the outside, from an external storage system, be it disk or a real-time stream, and all this data essentially has to pass through the whole memory hierarchy to the processor to essentially make sense of it. So we are back to basics. And so here I computed Amdahl numbers for different architectures. And we look at the last columns. So the Amdahl number is essentially the bits measured in I/O, or the I/O measured in bits per sec, and divided by the instructions per sec for a computer. Typical supercomputers have Amdahl numbers which are a few times 10 to the minus 3. And then normal computers in an academic setting have typically Amdahl numbers between 0.1 and 0.02, 0.08. And as an experiment, we built a machine called the Gray Wolf that is entirely aimed at increasing the Amdahl number using commodity components. But the beauty of the Amdahl number, besides its simplicity, is that one can not only assign an Amdahl number to a hardware by looking at the clock rate and the I/O rate, but one can also assign Amdahl numbers for a computational problem. And so this chart shows a bunch of the Amdahl numbers for different computational problems. And on the right, the dark green bars show typical data analysis challenges that we have performed on a database server. Then the green lines, the green columns correspond to problems that were performed on a bare-box cluster, which include, for example, image processing tasks of the phone and so on. And then the blue columns show supercomputer simulations done both in astronomy and material science. And what we see that there is an increasing gap between the hardware capabilities of the system and basically what also these different computational problems required. And I was puzzled that at this increasing difference until I also looked at the data set sizes. And it turns out that pretty much everyone, look at that, all the columns pretty much end in the range of 10 to 100 terabytes. So basically everybody gets stuck at 100 terabytes. And Pensas is the only data set that points beyond the 100 terabytes, but also Pensas has not quite reached today the 100 terabyte mark yet. It will probably in a few months. So summarizing this, what are the disputes today when we look at real scientific projects and the computational architectures? And the first thing sort of in your face problem appears to be simply the lack of this space. So, there is the saying in real estate, it's location, location, location. So here it is really about this space, this space, this space. And certainly our current problems are not on Google scale. So Google deals with 10 exabytes today. But we face problems on the 100 terabyte scale. So 10 to 30 terabyte projects are relatively easy. And 100 terabyte is on the margin of doable today. And 300 terabytes in a science project is really hard. And we need a huge sequential I/O bandwidth, but one of the primary problems is how do we move 100 terabytes within a university? Even if we only have a gigabit per second network, it would take 10 days. If we have a 10 gigabit per second backbone, then it would still take about 10 days or 1 day, but this means that nobody can transfer anything on the backbone. But if we drive a 100-pound box, then we can move actually 100 terabytes using SneakerNet across the university in a few hours. And if we need to move data in and out from the outside, it's really pretty much FedEx today. So what are the trade-offs? And when we talk about extremes and extreme computing, it's all about trade-offs. So I put together a tentative list of ordered priorities for such data-intensive science projects. And I would put today the top priority would be total storage with a relatively low redundancy. The second one would be cost. So what is the cost of the system versus the cost of the price of the raw disks that we need? The third component would be a fast enough sequential I/O that we, and I think today that the only way to do this cheap is to have locally attached disks with fast controllers. Then we have to be able to process the data streams also fast enough. So once we build a fast I/O, then also it doesn't hurt to have, for example, GPUs located directly inside the server. And then lastly, we do need to perform all this at low power. And of course, the order will be different in a few years. And also the scalability, how can this all be scaled kind of to multi-petabytes is going to show up. What's the cost of a petabyte? So this is from a website called backblaze.com. They put together this chart. So the price of raw drives, as of about a year ago, it was about $80,000. Then they built a homegrown chassis for about $117,000 with motherboard and memory and CPUs. If you buy the same system from Dell, they will charge about $800K. From Sun, it was $1 million before the Oracle takeover. And then if you buy storage at Amazon or in the cloud for 3 years, that would still be quite expensive compared to building it yourself. Not to mention if you want to buy a really expensive but fault-tolerant system, say from EMC systems. So we set out to build a Grey Wolf, and it's basically a fairly simple architecture, a Beowulf type cluster running Windows SQL Server, but running database, a distributed database system over it. So that's why we called it Grey Wolf, combining Jim's memory, giving tribute to Jim, and combining the Beowulf legacy. And basically, we were able to accomplish a fairly good I/O throughput, so about 70 gigabytes per second for about 46 nodes for about $700K. We built this 2 years ago, and we are already running out of space. So here is the concept. We put in a proposal to the NSF MRI recently to build a new instrument. This would not really be a computational system. It's better not to think about it that way. But how can we provide a place for people to bring in hundreds of terabytes of data and park it and analyze it for 6 months in a row, and then maybe take it away and then allow somebody else to use the instrument. And I think given the current state of hardware, for about $1 million, if we build it ourselves, we can build a substantially faster system than what's commercially available. So for about $1 million, we can build a system with about half a terabyte per second sequential I/O bandwidth and about 5 petabytes of storage. But what is most interesting is the storage dropout. So I asked for little project proposals from within Hopkins that who has scientific problems that they would be actually interested in using such an instrument if it was around. And the people put in proposals which totaled to about 3 petabytes. And this is the distribution of project sizes. Indeed showing that the stumbling block today is somewhere a little bit over 100 terabytes today. So I'd like to get towards the summary. So what are the short-term trends? We have large data sets, but we don't really have off-the-shelf solutions. We have a national infrastructure of computational facilities, but it currently doesn't quite match the power law. So we have a few very large supercomputers, and then we have some small clusters at universities, but we don't really have the intermediate tier of systems. And there is only just some of the data-intensive facilities are just starting to emerge, and today I think the best we can say is that they are probably just a little less CPU heavy than the previous generation, but certainly there's a trend in the right direction. What we see that high-performance projects are also choking on I/O. So some of the biggest simulations would like to store a lot more data than they currently can. Cloud hosting today is so expensive that is essentially, unless it's funded by the NSF in terms of these pilot projects, it's essentially not commercially viable for a university project. Also, the trade-offs of the commercial cloud computing are quite different from science needs, where basically a lot of it is around resilience. Scientists are cheap meaning that they don't want to, if I had $1 million, I would rather build my own system rather than pay it either to a commercial vendor and get 10 times less in terms of capabilities, or even with the current economic trends faced in the cloud. So we are still building our own. I predict that what we will see is a campus-level aggregation, because the broom closet idea that every group having their own DevOps cluster is not scalable to hundreds of terabytes anymore. And maybe what this will emerge, the economics of cloud computing will change. Obviously, it will have to change. So in this world, I think these campus-wide aggregations will become the gateways essentially to the commercial cloud hosting. So you only have to carry your data basically to the campus gateway, and then those places will have a fast, dedicated uplink to the commercial science cloud. So in 5 years, what we see is also there is a sociological trend in science that we see that data collection is happening in ever larger collaborations. Think of, LHC, the Virtual Observatory, NEON, or oceanography, you name it. And the typical properties of these projects are that the analysis is decoupled from the data collection, and it is mostly done off the archive data. And as the data sets cross over to multiple petabytes, then it will be increasingly important to have basically the computational infrastructure that enables the data-centric these computations and analysis performed on top of the data. So it is clear that some form, in 5 years, we have to have a scalable cloud solution for science is available, but it is the business model is still not clear, or who will operate it, on what scale, and how does the on and off ramp work. So how do we get the data in and out? And also we have to understand much better that what are the differences between the science needs for a cloud computing solution than from the e-commerce. And finally, we have to realize that scientific data will never be fully collocated. There will always be new projects springing up, and the geographic origin will be tied to experimental facilities. We will have to understand a lot more and spend a lot more cycles on streaming algorithms, data pipes for distributed workflows, and how can the data diffuse through basically this distributed computing infrastructure. And there is this intriguing idea coming from Ken Church and James Hamilton and Albert Greenberg, where basically we put data into containers and we move essentially petabytes by the containers across the continent.